My name's Reynold. I'm one of the co-founders at Databricks, and so known in the open source community for a lot of my work in Apache Spark. And today I'm super excited to be talking to you about how we realize the Lakehouse Vision to make data timely and more reliable. All right, let's get started. For the first part of the talk I'll be walking through some of the problems data analytics today actually stems from very complex data architectures the world has been sort of employing. And then I'll describe the Lakehouse technologies and how the architectural pattern and how that can actually remove this complexity by enabling much faster data warehousing, streaming, data science, and machine learning directly against the data lake storage. But before I dive into it, just in case some of you don't actually know about Databricks, we offer a cloud data platform for analytics, data engineering, and data science. And it was actually a spin-off company created out of UC Berkeley about 7 years ago. Right now, we've become, in mere 7 years, become a global sort of multinational company that's processing exabytes of data every day for over 7,000 of enterprise customers. We offer the product as an integrated sort of data platform. And of course, a lot of what we know about is for having created Apache Spark. But since in the past few years, we have worked on a lot of other open source projects like Delta Lake, MLflow. We also sort of acquired Redash and it's making it part of the platform. And so my thesis for sort of this entire talk is the biggest challenges today with data are focusing on two parts: data quality and staleness, which means your data are late or data are no longer recent, right? And it's actually not just me that's saying it. Fivetron, one of the leading sort of data vendors for data ingest, have done a data analyst survey, and they have found that 60% of the analysts reported data quality as the highest, the top challenge. And 86% of the analysts had to use stale data, so data that's old. And 41% of them are using data that are actually more than 2 months old, and sometimes actually years old. And 90% reported they regularly had to deal with unreliable data sources. So this is actually a really big problem. And as a different survey by Kaggle, which is a leading sort of data science competition platform, to reveal similar things. A lot of data scientists spend massive amount of the time that's trying to analyze and understand data. And it's actually significantly less time is spent on, for example, doing machine learning and or some maintaining infrastructure. So really this, the number one problem is how do we actually understand and analyze data? And the interesting part is, while getting high quality timely data is really hard, a lot of it has to do with the architecture of our own choosing. And part of it is really our own fault in how we made it happen. And in the rest of the talk, really the first half of the talk, I'll be walking through sort of the evolution of data management and why we are creating those problems for ourselves. So for a lot of you in the room, you probably, or in this sort of the conference, you probably are aware that data warehouses were started sort of in the 70s and 80s, and really the concept of data warehouses developed in the 80s and 90s. And data warehouses used to be the main repository for all data. You have data that's typically stored initially in operational databases like MySQL, Oracle, or Postgres, and they get ETL directly into a data warehouse in a batch-oriented fashion, sometimes daily, sometimes weekly, sometimes monthly. And then data warehouses are purpose-built for SQL analytics and BI. And there's actually a lot of functionality that's been added and invented over the years. Like there's a concept of schema, so you can actually better control the quality of the data, their indexes, and caching for performance. And data warehouses, after sort of decades of research and development, have built in very powerful management features such as transactions, and sometimes they give you the ability to do time travel. And it really became the standard starting in the 90s. Every large enterprise would have one and sometimes multiple data warehouses in which they try to store all of their data. And starting after sort of the year 2000s, and often pioneered by a lot of sort of the web companies like Google, we're starting seeing challenges with just using data warehouses as a main repository of data. And the main challenge is it's really hard for data warehouses to support the rapidly growing unstructured and semi-structured data. This could be talking about logs, images, documents, time series data. There's actually a very high cost of storing massive amount of data in data warehouses. Often the licensing cost is very high. They are not designed to quite work well with giant blobs. And more importantly, data warehouses were not designed to support machine learning and data science, which sort of the world are growing increasingly become sort of important. And there comes sort of the idea of data lakes. And the idea of data lake is you treat it as more or less a file system or a blob store, and you can actually dump everything you want into it. You dump all of your raw data into it. It's very low cost to store large amount of data. For example, in S3, you only cost $12 US to store a terabyte of data a month. And that's actually extremely cheap for cold storage. And the architectural pattern that's been developed is now we see sort of fairly common is enterprises will be loading all of their data and actually dump them into a object store like S3. And then so that become really the source of all of the raw data. And then once you have the raw data, you ETL a subset of them into, for example, a sequence of data warehouses for doing business intelligence. And that's often what gets exposed to analysts. And then there's, of course, also data science and data engineers that's operating, for example, data pipelines or doing sort of statistical modeling or even machine learning. For a lot of them, because the support in data warehouses is severely lacking, they would be directly reading the raw files using all of these machine learning libraries or data science libraries. And as a result, there's sort of this more complicated architectural pattern. Now there's actually multiple repositories of data have created different set of challenges. In addition to just simply being more complex to reason about, data reliability actually suffers. And the reason is the different storage system have different constraints. There's actually different semantics that's being offered. The SQL is actually slightly different. You might be thinking you're running the same, for example, the SQL query, but in your data lake implementation of the SQL engine actually has slightly different semantics from your sort of data warehouse implementation of the SQL. And then the actual ETL step that connects the different systems could also go wrong. Keeping them in sync is problematic. So there's just a lot of landmines. We've seen this over and over again. That's happening among our customers. Okay. The other part is sort of the timeliness also suffers because now you have different ETL pipelines that's stitching together all of this data and keeping them in sync. The ETL pipelines themselves might be down. Sometimes you actually forget to, for example, actually ETL a specific attribute, and the analyst comes by and asks, hey, I need that attribute is not available. Now you need to have coordinate with a very different team to actually create or update an existing ETL pipeline to get the attribute over to the data warehouses. So timelessness is also suffering from this. And as a result, really, sort of when you talk about data lakes, enterprises usually initially have very high expectation and think about sort of a beautiful lake, but it's becoming more and more of a data swamp, and really, it's just a lot of garbage that's flowing through the system, and it's very difficult to reason about. Just to recap, what we describe is some of the problems in more modern data architecture are actually due to a lot of the, I would say, system complexity. Some of it, but the complex system does have advantages. It does enable us to store in a very low cost fashion, large amount of historic data that otherwise would not be able to store it, right? But due to that, it's creating a new challenge that now we need to synchronize across the different subsystems data. So the question we started asking ourselves about sort of 3 or 4 years ago, after seeing a lot of different customers doing applying the same set of architectural patterns, and by the way, a lot of them use Spark to actually handle the ETL, is what if we didn't need to have all of these different data systems? Can we actually combine them as much as possible into one to remove the two challenges we're seeing here, the data quality challenge and the timeless challenge? So in the past sort of few years, we've been developing a set of technologies. And really, I would say this year, we are reaching the culmination of it, is what we're calling Lakehouse Technology. And Lakehouse is a collection of different techniques and feature sets to provide data warehousing capabilities directly on data lake storage. And we are not alone. There's actually a lot of other, I would say, companies recognizing this need, especially, for example, virtually every single, I would say, internet powerhouse. You think about Google, Facebook, Uber, many of them have applied the Lakehouse architectural pattern internally and developed independently a set of different technologies. But the key idea in Lakehouse is this three. The first is want to retain existing open file formats. And often it's Apache Spark or ORC. And the reason we want to be able to leverage open file formats is for to be able to leverage the large ecosystem of data science and machine learning tools. Because open file formats themselves are standards and a lot of other tools can depend on. The second part is to add management and performance features on top of this open file formats, on top of the data lakes, so we can support transactions, data versioning, indexes, and a lot of the data warehousing features that in many cases people take for granted. And last but not least is, can we actually sometimes help eliminate other data systems like message queues? But really the most important two factors are the first two, right? And we recognize after sort of thinking about this problem for a while, the two most important parts are a metadata overlay layer. And we have developed one open source system called Delta Lake. Another one is actually the new query engine designs. By combining sort of a good metadata layer and new engine designs, we're actually able to deliver best-in-class performance, ease of use, and management capabilities. They are like data warehouses on top of data lake storage. The Lakehouse Vision is pretty simple. You store all of your data in data lakes using a variety of open formats. It could be as simple as CSV files, but obviously for better performance, you want to store them as a columnar structure like Parquet. And then there's management capabilities, what I just talked about just now as a storage metadata overlay that give you transactions versioning. And then you have different sort of engines on top that all have the same view of all of the data. And the engines could be for streaming analytics, could be for business intelligence, could be for data science, could be for machine learning. But they all are connected and governed by the same platform against the same data. So it appears as a single platform for every use case. All right. And now we're going to sort of the key technologies that's enabling the Lakehouse. And the first I would be talking about is a metadata layer for data lakes. And the second is the query engine. And the third is how do we actually enable optimize access for not just SQL, but also data science and machine learning. So let's first start it with metadata layer for data lakes. And we didn't invent data lakes. Data lakes has been around for a very long time, for the past sort of decade or so. And how a lot of enterprises and sort of technologists view data lakes is just a collection of files. So it's a bunch of bytes and it's a bunch of files that's sitting on top of a file system. And then there's the query engine itself that tries to infer what are the semantics of those files. And what we are recognizing is a better way to view the data lake is rather than a collection of files, view it as a collection of data sets or tables. And you have metadata layer that can actually track which files are part of a table to enable much richer management features, for example, like transactions. And then if the client needs to or wants to, the client can still access the raw underlying files at very high speed by directly connecting to it. For example, you have a TensorFlow that can read Parquet. You should be able to read those Parquet files directly. This idea has actually been implemented by, I would say, 3 different systems by now. One is Delta Lake, the other one's Iceberg, and the third is Hive Acid. There's also actually a 4th one called Apache Hudi. Delta Lake is by far the most advanced and by far the ones that have the largest adoption. I'll be going into Delta Lake itself in a bit more details to explain the idea. And all for Delta Lake and Iceberg, both are keeping metadata in object stores itself. And for Hive Acid, it's actually keeping the metadata separately outside of object store in a database. There are different trade-offs. One of the main benefits of keeping the metadata in object stores together with the data is now you have a single atomic unit for all of your actual tables. Whereas if you keep it in a database, now it's actually much harder to move the stuff. So before Delta and before all of this, if you look at a data lake, it is pretty simple. You have a collection of files that compose a table. For example, in this case, events table. Let's say we have 3 files: Parquet 1, file 1, Parquet 2, and so file 3, right? Now, this seemed to be okay, except there's actually a lot of underlying issues. By the way, this has been basically how I would say the world works for the past 10 years. Is if you use Hadoop or to be conducting a data lake, you store a lot of files in S3. Before Delta, it's just a collection of files. Now, a lot of the concrete problems people run into are what happens, for example, when you want to delete all events. That's about customer 13. For example, maybe due to GDPR, you get a request, you must wipe all of those data. Here's how it typically works. You look at the file 1, and then you find all the data related to customer 17, and then you generate a new file, a new version of file 1 that wipes all of that data. And then you delete file 1.parquet itself afterward. So file 1b replace file 1. And then maybe you go to file 2 and realize file 2 doesn't contain any data for customer 17. And you look at file 3, and it does contain it. So you do the same thing. You generate the 3b version and replace 3. Now, the problem comes along that, hey, what if you actually have a bunch of read jobs that's trying to read the table while the delete job itself is running? Multiple things could happen, but one concrete scenario is the query is actually trying to read, the read query comes in when file 1b is generated, but file 3b hasn't been generated yet, and file 1 hasn't been deleted. So you actually started seeing a very inconsistent view of the data. Maybe because customer 17's data is partially deleted, or maybe in some cases, worse because some other customer's data has now been duplicated because it's reading both file 1 and file 1b. It really all depends on the timing. There's no strict control of what the reader is reading. And the other one is, what if the query that's during the delete actually fails halfway through? It's even worse than the first scenario because now you might have a permanent corruption of your table. To work around a lot of these problems, we have seen different users doing very different things. Many of them, for example, use the partition boundary as the way to mitigate this problem. If a job fails, you rerun it across the entire partition, but it becomes very, very complicated. If you think about how this works in a data warehouse, the way it works is very simple. You issue a simple delete query, and then the data will be consistent, and no read jobs would fail because there's a concept of transactions. So here's actually how Delta works. In Delta Lake, the events table still contains a list of Parquet files. But in addition to those Parquet data files, there's actually a Delta log directory. And in it, we're storing the transaction log of what's been happening to the table. And the delta log really is the authoritative truth, a source of truth for what files are actually part of which version of the table. All right. So maybe the V1 is actually a specific version of the table. V2 is another version. And V1 would say, hey, there's actually 3 different files, and V2 maybe 3 different other files. So in the case of a delete query comes in the same example, want to get rid of data for customer 17, we'll be doing it's a similar thing we're doing in the rewrite. We'll generate a new file, 1b.parquet. The same thing we generate 3b.parquet to replace 1 and 3. But there's actually now atomic operation. So we don't actually delete those files first, but we generate now v3.parquet that tells Delta Lake, hey, the third version of the table has 3 files. There are file 1b, file 2, and file 3b. All right. And when the reader comes in, the reader could decide which version of the table to read. The reader could be reading version 2, could be reading version 3. If the reader is actually reading version, for example, 3, it would see here's actually a consistent result that's after all of customer 17's data have been deleted. If the reader is reading version 2, you see everything with together with customer 17's data. So now you actually get a strong consistency. The reality is a little bit more complicated than just a bunch of Parquet files because we have done a lot of performance optimizations. You don't have to always rewrite entire snapshots. But here's sort of a slightly simplified version just for explanation purposes. Right. If you want to understand more about the Delta Lake itself, we've recently published a VLDB academic paper about it. Delta Lake high performance ACID table storage over cloud object stores. It went into a lot of details about how Delta Lake works. And it's also open source project, so you can even look at the just the GitHub by searching for Delta Lake. It is part of the Linux Foundation project. I would encourage you to check out more. Really, so in the past, we developed the Delta Lake about 2.5 years ago. And now more than half of all of the data that's manipulated on Databricks are stored in Delta Lakes. There's actually more features that I haven't even talked about. So we mostly cover on how it works in transactions. But building on top of a transaction log, we're now able to sort of develop even more functionalities. Like, for example, because now we have different versions of the same table, would enable the ability to time travel into an older table version. So customers could actually say, hey, timestamp as of a specific date or specific version. And we also allow zero copy clone. If you want to, for example, sort of copy a very large table that's a petabyte, instead of cloning the entire table, you could just create a new table. And then the new table is actually referencing it has its own Delta log, transaction log, but it's referencing the same data files of the old table. Because the transaction log itself has a history of all the changes that have been made to the table, so now you can actually describe history and see what happens, which user have done what against the specific table. So it's quite convenient. And last but not least, we've implemented all the basic DDL statements you would be expecting out of data warehouses. You can insert data, you could call upserts, you could delete without sort of having to worry about data loss or corruption. You could also run merge statements. So this is incredibly useful for example, GDPR or just evolving your data sets. And that's not even it. There's more. For example, you could actually treat the table itself as a stream of changes. And in some cases, we've seen so people removing Kafka with a Delta Lake table. The idea is Delta Lake is not designed to replace Kafka. It's not a message bus by any means. The latency will be significantly higher than the message bus. But if you are just using Kafka, for example, for change data capture, Delta Lake is actually a much better way of doing it. And then because now we have the transaction logs that actually describes what the table is, and along with the schema information, we can now actually enforce schema as part of a Delta Lake. And we can also add expectations or constraints on the Delta Lake table. So for example, you could say, hey, a discount, like a price has to be greater than 0. If you're applying discount, it needs to be less than the listed price. And all of this are actually built-in, you can actually use it today. As I said earlier, just on the Databricks platform alone, Delta Lake has been used by thousands of different organizations to process exabytes of data every day. It really grew from sort of a 0 in 2.5 to 3 years ago over to about half and more than half of the workloads on Databricks. And some of the largest deployments have exabytes of tables, and so thousands of users are using it daily. Right, and this is just what we can see on top of Databricks, because the open source project is probably a lot more that we don't see. It's also available with a lot of different ecosystem. You can store them in store Delta Lake in pretty much any storage system, and there's different ways about getting data ingested into it. You can query it from a lot of other systems as well, even outside of Databricks. The second thing I want to dive into is sort of new query engine design, aimed at enabling great SQL performance on data lakes. So there's a school of thought that it's impossible to get great SQL performance out of sort of open data lakes or Delta lakes, because data warehouses have full control over the storage system and query engine, and they design them together. And if the key idea in Lakehouse is to store the idea in open storage format, how can we actually get great performance compared with sort of a closed system, right? Because closed systems seem to have less constraints. And our thesis a few years ago is there's actually no fundamental reason that we can't get great performance out of openness. And as a matter of fact, we could apply the similar techniques that's applied to the closed systems to get the best performance. And in particular, I'll be talking about 4 specific optimizations here. One is caching, the other one's auxiliary data structure, third one's data layout, and the last is a vectorized execution engine. These are all important techniques, I would say, data warehouses apply, especially in modern days. And we can apply techniques in very similar ways to Lakehouse. And we have been developing this product called Databricks Delta Engine in Databricks, which is effectively a new query engine that employs all of these ideas. So first is caching. If you sort of look deeply into it, most data warehouses, the workloads are sort of concentrated, have a very strong time pattern. They tend to access sort of a similar set of data, and they are hot. And in order to optimize for that, data warehouses use of solid-state drive. The states often NVMe SSDs and memory to improve performance. They cache the data so you don't have to, for repeated scans, they don't have to go to the source of the data like disk. As a matter of fact, we could actually employ a similar technique in Lakehouse now, especially with the metadata layer. Especially when the metadata layer can tell us whether a table has been updated, so we can do a caching validation. Because, for example, often Delta Lake data are stored in S3 or object storage, which have limited throughput to or bandwidth to the actual nodes during the data processing. Caching those data locally is highly beneficial. So Delta Engine actually have a caching layer that the caches the data in a very different format, because once they get into the SSDs, it's less I/O bound. So you apply, for example, less compression, and that will be faster for the CPU processing. And when we benchmark it, you can actually see substantial performance gains compared with, for example, just storing vanilla Parquet on those the same NVMe SSDs, or especially compared with Parquet, reading from S3. The second thing is auxiliary data structures. One of the complaint and one of the problem with Parquet is it's quite limited. It's just a columnar structure and doesn't actually give us a lot of statistics or information is needed for our performance. But even though we store the data as Parquet, because now we have this transaction log, we could actually store more information, they're auxiliary, in the sort of the transaction log. So in Delta Engine together with Delta Lake, we have a bunch of our Parquet files. We'll be collecting, for example, the min max value for each of the column. And then when there's a query that's executed against this data set, we'll be looking at the filter predicates, in this case, year and UID. And then we'll be sort of first, instead of going directly to the data, we'll be looking at the transaction log to look at whether we can prune any files before even reading them. So for example, if the predicate is year 2020, we can skip all of the data where the max year is actually less than 2020. And this statistics can be updated transactionally in the delta log itself. So it's always consistent with the the data itself. Right. Now with this, we can actually do data skipping much more effectively. But some of you that know more about, spend more time optimizing data layouts, might realize, hey, we could give you data skipping, but then data skipping, having the capability to data skipping doesn't actually mean you could skip the data well, because if your data is not clustered or it's not well arranged, it's actually problematic because you might have, for example, year 2020 in every single file. The simplest way to do this is in a lot of data warehouses is a way to do specific clustering or sorting. But you can actually do the similar techniques using Parquet files. Parquet is just a format. It doesn't dictate, for example, exactly how you would be clustering the data within those files. So one simple thing we could do is to actually sort the table, for example, by UID for fast access. But one problem with that is sometimes you actually have a table in which you want to apply multiple dimensions to do filtering, for example, both the UID and the year. So we introduced this concept of Z ordering for multidimensional access. And Z ordering actually allows, it's a very unique way of doing sorting that gives, instead of different weights, to different columns, it gives roughly equal weight for clustering to all the columns. So now you could actually skip on all of the columns in a similar way, unlike sorting, which only works really for the first column. All right. And we've actually done a new generation of Z ordering that's based on Hilbert space filling curve. It's actually giving even better results. This is actually, we talked about this in the Delta Lake paper. And last, but not least, probably the most important thing is the vectorized execution engine. A lot of the modern data warehouses, especially started in, I would say, the year 2000s, have employed vectorization as a technique. So they arrange data in columnar format, just like Parquet and Delta Lake, but they also do the query processing itself in a columnar batch fashion using SIMD instructions that are available in part of the modern CPUs. And we have looked at, done extensive study and research, and a lot of prototyping eventually led to a new execution engine as part of a Delta engine called Photon. And that applies exactly the same set of optimizations. And then the results, we actually talked about this in Spark Summit just a couple months ago. The results is phenomenal. We could achieve a 10x performance improvement than the JVM-based engines like Apache Spark or Presto. And we'll actually be going to a public preview fairly soon with this new vectorized engine. So we talked about a lot of different optimizations. You might be wondering, so exactly what does it look like? We understand it's probably much faster once you apply them than just vanilla Spark or Hive or Presto. But once you put everything together, given that most reads are actually reading from cache rather than going all the way to, say, the data lake S3, because most reads are repeated reads. And I/O cost is a key factor for non-cache data. And the third is CPU time can now also be optimized with vectorized processing. It's actually not surprising, theoretically, a Lakehouse engine can offer similar performance as data warehouses. By doing it really, really well and putting it together, we are benchmarked against different data warehouses, sort of the 3 leading data warehouses products. And we actually achieve similar performance as the fastest one in the TBCDF 30 terabyte benchmark. We'll be reviewing more in the coming sort of weeks and months about the details of this benchmark, so you can actually dive in more into it. But here's to give you a teaser, and I'm personally very excited about this specific thing. All right. Last, I want to talk about quickly about optimized access for data science and machine learning. The key idea is it's really painful to doing sort of it's really painful to be doing machine learning over data warehouses. And often people just do them by exporting the data to a data lake. That actually makes it even more complicated because now you have to track data outside of data lakes. But ML over the Lakehouse is much simpler and much more straightforward. You have direct access to the underlying data files without overloading, for example, your query engine. You can just go straight to the source of truth. And most of the ML framework can already read, for example, Parquet files. But we've done even further by making so ML easier with this, and a lot of the work actually happening in Apache Spark itself, because a lot of machine learning is about data prep, and data prep requires sort of using a structural API in Python and R to be preparing that data. So Spark's DataFrame API is designed exactly for that. And you even have a great advantage that when you're working with large amount of data, it's declarative. So you would actually take in your entire query plan and then decide how to optimize it. And you can leverage even the similar set of optimization which talked about for the ADELTA engine in the Lakehouse, running SQL queries, caching statistics and all that. So you get great performance. And then you can actually put it into the TensorFlow or your PyTorch to be doing training. And then the management features actually make this even nicer. Like, for example, sort of a common problem in machine learning is how do you actually do governance and lineage tracking. And then with the time travel feature of Delta, now it's very easy to make a model reproducible because you just take the data version, you save that, which is just a single number of the version rather than saving the entire data set. And then you have your training code, skid hash, and now you have reproducible experiments. Right, and there's a lot of other different advantages of this as well. So just to summarize the talk, so we talk about a lot of different pieces, but really I want you, I think the most important takeaway is Lakehouse is a new sort of a set of technologies and patterns that combine the benefits of data warehouses and data lakes. It provides via a new metadata layer like Delta Lake, a bunch of management capabilities on your table. It allows you a single source of truth storage for all of your data. And you can deliver great performance for SQL and BI with new query engine design. And we went into the details here. And it provides direct access using open file formats. And it's extremely low cost because the cost of storage is the same as the cloud storage, which, as we talked about, is somewhere between $12 to $30 per terabyte per month. We really see this as an evolution of the data architecture for everybody. And in the next few years, we'll be continuing to be working on improving the technology to make sure they are mature enough to capture all of these different use cases, from machine learning to data science to BI to streaming analytics. And the result is we have significantly simplified data architecture to improve both the reliability of data and timeliness of data. So here's sort of, before I sum up, here's sort of before picture of Lakehouse. You have a lot of different ETL jobs. You dump them into data warehouses. And you have different copies of the data. And in Lakehouse, you would just have your data in the cloud object stores. It's really low cost. And then you can have serve all of your different use cases directly out of those. All right. Now you have fewer copy of data, fewer ETL steps, and there's no divergence. So to learn more, you can actually go to Delta Lake's open source project website to look at it. There's also a lot of free content if you're interested in diving more at sparksummit.org. There's a lot of things I talked about are capturing different pieces in the June Spark Plus AI Summit and also in the November Data and AI Summit Europe. And all the videos are available. So with that, I would like to just thank you